In this video, I'm going to show you how to derive the Dirac equation from group theory, specifically the Lorentz group. The process works roughly like this. First, one writes down the Lorentz transformation property of a vector, and then recasts that Lorentz transformation property. This recasted version of the Lorentz transformation property of a vector allows the identification of two new representations of the Lorentz group, the left-handed and right-handed vial representations. From here you can build the by spinor representation and then work out the minimal, meaning simplest, Lorentz invariant Lagrangian density, which ends up being the Dirac Lagrangian density, and its equation of motion, of course, is the Dirac equation. So that's how it works. It turns out that this minimal Lagrangian density is also the only one that yields physical results, that is made out of Dirac spinors. Of course, this discussion here makes it seem really simple and straightforward, and in a sense it is really simple and straightforward. In a sense there isn't much to it, though it turns out that the actual math of doing it is surprisingly intricate and somewhat complicated looking. I write it all out in complete detail and explain all of it as I go. And most of the explanation I give is actually written in words on the screen, so if you have trouble hearing for some reason, or if you just want to follow along with what I'm saying, perhaps seeing it written down also helps you take it in, then most of what I say, barring some ad-libs that give additional information, is written along with the math in a useful way. So now follows the math section. The entire process of extracting the Dirac equation from group theory, specifically the Lorentz group, begins with the well-known transformation property of a vector field under the Lorentz group. The vector transformations are given here in terms of these lambda tensors, which are equal to natural exponentials of quantities proportional to group parameters contracted with generators. These are the generators of this particular representation. The basic strategy is to recast this transformation relation in a creative way, and then use that reformulation to reveal a few new closely related representations of the Lorentz group. After this, the strategy is to define a massive field that transforms via the action of a particular one of these representations. Specifically, the massive field will be a Dirac field, and it will be assembled out of massless fields called vial spinor fields, which will have been defined previously. Then the Lorentz invariant action of this field can be deduced. The action turns out to be the action of the Dirac equation. The Dirac equation then comes out as the corresponding equation of motion. Now for the recasting of the old Lorentz transformation relation for a vector field, if one adds the identity matrix to the set of Pauli matrices in this way, where A and B are the matrix indices, then one can recast the transformation property of the vector field in a useful way by contracting it with this 4-vector of matrices and then transforming the result. First, the contraction. This gives us this MAB matrix here, just choosing to call it M. Now let's Lorentz transform A mu and see how M changes. To do this, it is easiest to first consider an infinitesimal Lorentz transformation. Seeing as we're dealing with a covariant vector, we need to Taylor expand this lambda inverse tensor and then take the limit that omega is very, very small, and therefore you only get the term linear in it surviving in addition to the constant term. And of course the thing we're expanding and taking that limit on is just the expression given up here with these generators, where these parameters are antisymmetric. For such an infinitesimal Lorentz transformation, we have this value for the change in the vector field and this value for the change in the MAB matrix. We can rewrite the change in the MAB matrix, this delta MAB, in a different way by first rewriting this quantity in the parentheses in a different way and then sticking this minus the vector back on it afterwards. So this quantity in the parentheses can be rewritten in this manner in terms of these matrices here, these SL mu nu tensors, which are defined in terms of these sigma mu and sigma tilde mu quantities, which themselves are defined in terms of the identity and the normal Pauli matrices. It is straightforward to verify this alternative way of writing this quantity by plugging in the values of these two tensors. Then straight simplification reveals that this does in fact equal that. If one then inserts this into the relation for delta MAB, one finds this quantity here. Now one can read off the finite form of this transformation from the infinitesimal version. It just works out to be this if we take the L and R matrices to have these values here. It is readily apparent that this has to be the finite form of the above transformation relation, because if one Taylor expands it and then takes the limit of small omega, meaning ignoring all terms of higher power than linear in omega mu nu, we arrive at this value for the infinitesimally transformed MAB matrix, so then we get delta MAB. No other finite form produces this infinitesimal transformation. One can see that these new transformations L of omega and R of omega are related by an exponential map to what appear to be generators. These tensors SL mu nu and SR mu nu look weirdly like generators when you look at them in these new L of omega and R of omega thing. It looks like they're generators of some Lie group. Direct commutation shows that these generators simply satisfy the Lorentz group algebra. So in fact, they are just generators of two new representations of the Lorentz group. So this recasting of the vector transformation relation has revealed two new two-dimensional representations of the Lorentz group. One can now define fields that transform under the Lorentz group via the action of these representations and explore their properties. Psi L is called a left-handed Weyl spinor and psi R is called a right-handed Weyl spinor. These relations are in accordance with standard convention. It is well known from study of the rotation group that for a spin-half field under infinitesimal rotation, we have this change. One can see from the above values of L of omega and R of omega that this is exactly how psi L and psi R dagger transform. Therefore, these Weyl spinors are spin-half fields. It turns out that one can assemble another particularly useful reducible representation of the Lorentz group called the bispinor representation out of these two Weyl spinors. Fields that transform under this representation are called Dirac spinors. Specifically, if one defines a Dirac spinor as follows, out of these left and right-handed Weyl spinors, then the Lorentz transformations of this quantity are obviously generated by this matrix, this 4x4 matrix here, given the known transformation properties of these two Weyl fields that compose the Dirac field. So explicitly, the Dirac spinor transforms as follows under Lorentz transformation, where we just take this as the generators. It turns out that there is an alternative way to express these generators that is much more useful, which can be accessed by defining a new set of matrices called the Dirac gamma matrices. First, remember the value of the SL and SR tensors. Given these values for the SL and SR tensors, the following relation is true if we take gamma mu to have this particular value. You can literally plug it in and just see in your head that it in fact does yield those values for the SL and SR tensors. Oh, and by the way, this representation of the Lorentz group that the Dirac spinor transforms under is called the bispinor representation. I don't think I've said that previously. One can express the generators of this new representation quite compactly as just sigma mu nu over 2. And we find that this sigma mu nu over 2 in fact does satisfy the Lorentz group algebra. This verifies that we have just built another representation of the Lorentz group out of the previously studied smaller ones. Using these new and useful expressions for the generators of this representation of the Lorentz group, the Lorentz transformation relation of the Dirac spinor can be expressed like this. This exponential right here is the bispinor representation of the Lorentz group. Because the Dirac spinor is simply a column vector of Weyl spinors, it's obviously a spin-half field. Another key property of these matrices, these gamma matrices, is that they anti-commute to yield twice the metric of the group. of course, times the identity to handle the matrix indices and the gamma matrices. So with this done, it is now time to look for quantities with transformation properties that might facilitate the construction of a Lorentz invariant action. In an effort to find Lorentz invariants made out of the Dirac field, one might guess that psi dagger psi would be invariant. It, however, turns out not to be so. First, let's make the following definition. I define this S of lambda matrix just to make it so that I don't have to keep sticking this everywhere, this exponential, which would make things look much more complicated unnecessarily. Then we have this transformation relation and then this Hermitian conjugate transformation relation. With this definition, the transformation relation of psi dagger psi can then be written here, which would be an invariant if S dagger were equal to S inverse, but it's not. In order to figure out what S dagger does equal in terms of S inverse, first we need to note this identity, and then apply it to working out what the Hermitian conjugate of the commutator of gamma matrices is. Through the algebra, you see it just turns out to be negative, the same thing sandwiched between gamma 0 matrices. Then we can remember that sigma mu nu is proportional to such a commutator, and then we can apply this identity for the value of the Hermitian conjugate of such a commutator to the effort to evaluate what S dagger is in terms of S inverse. And we see that it's just S inverse sandwiched between gamma 0 matrices, where the middle relation here is manifestly obvious if one considers the Taylor expansion and the fact that gamma naught squared equals the identity. If we Taylor expand, the first thing we get is a constant term, just the identity matrix, so then you end up with just these collapsing together and squaring to the identity. So then it matches with what you get from Taylor expanding this side for that first constant term. Then for the second term, which is linear in the argument, we simply get that linear term sandwiched between these two, which is exactly what this linear term turns out to be. Then in quadratic and higher terms, you end up with multiple powers of this on this side and multiple powers of this sandwiched between these two things on this side. And that would be a problem if the gamma naught didn't square to the identity. That way all the ones that would stop this from equaling that end up squaring to the identity, and you end up with some number of powers of this sandwiched between two external gamma naughts on both sides, so it ends up being absolutely equal. Therefore, psi dagger psi actually transforms like this. The goal now is to figure out how to modify this so that one arrives at a Lorentz invariant quantity. It turns out that the modification required to make this Lorentz invariant begins with defining a new quantity called psi bar, which is just psi dagger gamma naught. And this is actually a really clever quantity. You'll see how it brilliantly fixes the problem. One can then show that psi bar psi is Lorentz invariant. So if we remember that psi bar psi is just psi dagger gamma naught psi, and then Lorentz transform it, we get an S dagger here and an S here as before, and then we plug in the formula for S dagger in terms of S naught, and we see that these are going to cancel, and then these will cancel against each other, and then psi dagger gamma naught is just psi bar, so then we have psi bar psi, which is what we started with. So this is definitely Lorentz invariant. One can also construct a useful vector under the Lorentz group out of the Dirac spinors. Specifically, one can show that psi bar gamma mu psi transforms under Lorentz transformations like a vector, so like this, where these lambda tensors have the same values as given at the beginning. So in short, one can show that S inverse gamma mu S equals this lambda tensor contracted with that gamma matrix. And the reason why this is necessary for these to transform like vectors is because we already know how psi bar and psi transform, so we can transform this quantity. And then we see that in order for it to actually equal this gamma mu sandwiched between these two S of lambdas has to have that value, otherwise these relations aren't valid. To begin proving this, we first need an identity that seems irrelevant. We need to prove that this equals that, and I've shown the algebra required to do that. And then we can apply that repeatedly to prove that this quantity here equals this. Then we can contract this with this on both sides of the identity we just derived, and ultimately arrive at this commutator contracted with these group parameters equals this value here. So then we can look at an infinitesimal transformation, and using this identity ultimately work down to the fact that this really does just equal the infinitesimal version of this lambda matrix here. Now, because the finite forms that produce these infinitesimal transformations are unique, we can then see that the finite form for this relation here has to be this. Thus, we've proved that key relation, and therefore that this thing really does have these transformation properties. Now we know that the 4-vector partial derivative d mu under Lorentz transformations, of course, does just transform like a vector here, where of course these lambda tensors are the same as was given at the beginning, because it's still just a vector. One finds then that this quantity here involving derivatives of psi is Lorentz invariant through this sequence. So first we see that this comes in for the index on the partial derivative, and then we've got this S inverse and this S coming in from the Lorentz transformations of the Dirac field. Then we recognize that this S is a constant and can be pulled through the partial derivatives, and because this is just a number, it can be pulled through that as well. So then we arrive at this quantity, which we've just proved has this value up here. So then we arrive at this, but then these are just matrix inverses, so they turn into a Kronecker delta, which then just leaves us with exactly what we started with, where dummy indices were relabeled freely as required. So with this, it is now apparent that the minimal, meaning simplest Lorentz invariant Lagrangian density containing a kinetic term and a mass term is simply this, where the factor of I was inserted to make the corresponding Hamiltonian Hermitian. Additionally, this is also the only Dirac fermion Lagrangian density that yields sensible physics. Computing the equation of motion then just yields the Dirac equation in natural units, thus completing the derivation of the Dirac equation from group theory. There are, however, a few more things that need to be said about this, just some additional information about group theory and its relevance here. So far, the chiral representation of the gamma matrices has been used, but when not working with Weyl fermions, it is usually customary to use the Dirac representation, which also satisfies the same anti-commutation relations, and produces a perfectly functional set of Lorentz generators for the bispinor representation through the commutator formula given above, and re-expressed here, where these generators of course satisfy the Lorentz group algebra when you use a different representation of the gamma matrices as well, so long as they satisfy this key relation. None of the above relations involving the Dirac gamma matrices required that any particular representation of the gamma matrices be used for their validity, except for those that explicitly depended on the bispinor representation being in block diagonal form. This corresponds to the chiral representation, which only included the portion that served to show the relationship between the bispinor representation and the chiral Weyl spinor representation. Look back at the math that we've covered and see that this is true. Because of this fact, this anti-commutation relation is usually taken as the definition of the Dirac gamma matrices. This relation is called the Dirac-Clifford algebra. In general, for groups that admit spinor representations like the Lorentz group, one can postulate a set of objects that anti-commute to yield twice the metric of the group, and then commute them to yield a spinor representation of the group via this formula. The chiral representation of the Dirac gamma matrices was merely the one that most naturally came out of the group theory in this approach, because in this approach the Weyl representation was discovered first, and the bispinor representation was then constructed out of them. Any other solution to these defining anti-commutation relations would leave everything fundamentally unchanged. It would simply represent a non-block diagonal re-expression of the same math. Additionally, while the Dirac spinors transform by the action of a reducible representation of the Lorentz group, they transform under an irreducible representation of the Poincare group for the massive case. For the massless case, Dirac spinors are again reducible. One can then go from the Dirac representation of the gamma matrices to the chiral representation used in this document to decouple the two helicity sectors of the massless Dirac equation into the two Weyl equations. So now you've seen the comprehensive mathematical treatment of the problem that is the derivation of the Dirac equation from group theory. Hopefully this interested you. Hopefully it was easy and clear to understand. Hopefully there was nothing that felt mysterious about the process. And my hope is that this approach to arriving at the Dirac equation provided you with a more satisfying alternative to the ordinary way of doing it, which is square rooting the Klein-Gordon operator. Hopefully it shows you a more satisfyingly rigorous way of arriving at the Dirac equation directly by studying the Lorentz group. Dirac out.